So this is the last video lecture of the year. Yeah, over, yeah, thank you. Last one of the year that's over new stuff. I may still post some, just for review, but those are optional, right? Those are just reviewing for the AP exam. So, electrolysis. This is going to be kind of a tricky one. Yeah, I got to go out on a high note, right? So, I'm going to try to cover all of this in one video if I can. There is a lot here, okay? And some of this is you're more likely to see on the AP exam than other parts of it, so I may really, speed past some of it, but I'll probably still mention it. One thing that's on your notes, the section 27 and 20.8, the batteries and corrosion sections, I never have time to really discuss those the way that I would like to, because it's really applicable. It's interesting stuff. I mean, if you're into cars at all, or how batteries work, that sort of thing, those sections are really applicable. So I put the page numbers on the notes in case some light reading later. In case you want to go back and read those. I just don't have time to cover them right now. Okay, so we need to jump into electrolysis, because if you get the voltaic cells, you'll be able to get any sort of battery or corrosion question that they would throw at you on the AP exam, because you already understand the theory, okay? Those sections are just a little discussion of the application, but electrolysis is different, okay? So and this is something else that they might throw at you on the AP exam, so we need to talk about this. So first question here, is it possible to make a non-spontaneous reaction occur? If a reaction is not spontaneous, does that mean it will never ever happen? Not necessarily, okay? What's the definition of spontaneous? Okay, occurs naturally. Okay, the key there that we said on the notes before, it occurs without ongoing outside intervention. You remember that terminology? It's kind of important, okay? So, if we want to make a non-spontaneous reaction occur, we need to provide ongoing outside intervention, right? And what do we mean by outside intervention, really? How are we intervening, probably? Well, spark would be an example of starting a spontaneous reaction, and then it keeps going on its own. Okay, so that's the initial intervention that we might have to provide, but there's no ongoing intervention required. Okay, ongoing intervention would not be just a spark, but you have to continually be pumping energy in some form into this system. And as soon as you stop pumping energy into the system, what happens? The reaction stops, right? Okay, so it's not one of those things where you can give it a spark and it'll keep going on its own. This is something we're talking about where you have to keep pumping energy into it continually. If you don't, the reaction stops, okay? So, continual addition of energy is really what we're talking about here, okay? So, if we want to make a non-spontaneous redox occur, we can use electricity, okay? We're continually passing electricity through something. That's that continual addition of energy that can make a reaction happen, even if it's non-spontaneous, okay? This is called electrolysis. And you have to have an outside source of electrical energy for this to happen, okay? And these reactions take place in what's called electrolytic cells. Looks like electrolysis, so that hopefully makes sense. There are two types of electrochemical cells you need to understand for the AP exam, okay? The one is what we've been talking about the whole rest of this unit. Okay, that's the voltaic cell. That's the spontaneous redox reaction. That's a battery. Okay, and a battery is basically, in order for a battery to be a good battery, it has to happen spontaneously. It has to provide electrical energy. Okay, an electrolytic cell requires electrical energy. You have to put electrical energy into it to get it to work. Why would that ever be useful? Why would we ever want to pump electricity through a system to make a redox reaction occur? I mean, isn't that the point of redox, is that it occurs so that the electrons flow and then we can harness that energy? okay, maybe for a rechargeable battery, and essentially what that does, it's going to reset it to its initial state, right? So in a redox reaction, what we talked about the other day is eventually these things will continue reacting until they reach equilibrium, right? And at that point, the E0 for the cell is 0, okay? The standard EMF is 0. And then it's not producing any voltage anymore. So to get it back to its original state, we might have to provide some electricity to recharge the battery, okay? So that's one example. Another really good example will actually, well, I guess we can talk about it right now, okay? Usually in an electrochemical cell, you're going to have 2 electrodes in a solution or a molten salt, okay, just kind of depending. So solution, we're talking, something dissolved in water. A molten salt, we're talking about you take sodium chloride, you melt it, okay, and then you just have sodium Na plus ions, Cl minus ions, because it's a molten salt. There's no water in there at all, okay? And then you're going to need a battery or some source of electrical current that's going to push the electrons in one specific direction through the cell, okay? So here's an example of an electrolytic cell. Sodium chloride, which is the example that I just said. You've got a molten salt here, all right? So you've got, you've just taken this sodium chloride and you've melted it, all right? And now what you're doing is you're pumping the electrons through this cell using a voltage source, okay? This is, maybe this is plugged into the wall or something like that, okay? And it's pumping electrons through this cell this way, okay? So then what's happening is, as these electrons go through this cathode, now the cathode could be anything as long as it's not participating in the reaction, okay? But this cathode, the electrons are going through it, okay, and they're hitting the Na plus here. And as they do, you can see that the sodium then gets reduced, okay? Which is not normally what would happen spontaneously, okay? This is not typically going to happen. Sodium, solid sodium, we've talked about this before, very reactive, right? So you will find very little pure sodium in nature, okay? Because sodium tends to be oxidized, right? Okay, but if you have Na+, if you pump enough electrical energy through it, you can get it to change back to just sodium, the element, okay? Now, why would that be useful? To be able to make pure sodium. Okay, I mean, for one thing, in our chemistry labs, right? Okay, there are times when we like to just cut a piece of sodium, drop it in some water, and show what happens, right? So there are scholastic and commercial uses for solid sodium. Okay, probably more scholastic than anything. But there are times when solid sodium is useful. So being able to make solid sodium, and this is really one of the only ways that you can actually make it. Okay, and this is tough because you have to get an ionic compound very, very hot before it will melt like this, right? So this is taking place at very high temperatures. Okay. And then on the other end, because the electrons are being removed from the chlorine is actually getting oxidized here, which again, not a typical thing that chlorine would want to do, okay? But if you are providing enough energy, you can force this to occur, right? So that's the idea with electrolysis. And then here, you're going to make chlorine gas, okay, which again, can be used industrially. So there is some usefulness to each one of these particular reactions. All right. So the half reactions that occur, well, I just showed them to you, but I guess we can rewrite them here. So you've got the sodium being reduced to Na plus 2 electrons yields 2 Na, and at this high temperature, that's going to be a liquid. As you allow that to cool, it's going to solidify. Okay. And then you've got 2Cl minus yielding Cl2 gas plus 2 electrons. Okay. And the reason that these are all 2's up here, again, is because when you add these two together, remember the number of electrons being lost needs to equal the number of electrons being gained. Okay. So those are your 2 half reactions. The overall reaction here is 2 Na plus plus 2Cl minus yields 2 Na liquid plus Cl2 gas. Alright? And that equation should be balanced both in number of atoms and in charge. Alright? So again, it might not seem like the most useful reaction at first glance, but there are some things that we can use pure sodium and pure chlorine for. And so that might be a useful reaction. And again, electrolysis of molten salts is a good way to make a pure active metal such as sodium or aluminum. Now you can probably think of some very good uses for aluminum, okay? And this is a way that we would also make pure aluminum. Aluminum is typically found in nature in compounds. It's usually oxidized, okay? Because it's fairly reactive. Okay, how difficult is it to melt an ionic compound? We just kind of talked about that, right? Let me see if it's here in the book, the typical temperatures that you have to use. That doesn't really specify, but usually I think I'm correct in saying it's anywhere from 500 degrees Celsius to about 1,000 degrees Celsius. Somewhere in that range to melt an ionic compound, okay? Which, you know, that's fairly difficult, right? So, I can think of a better way to get sodium and chloride ions than melting salt. What's a better way to get sodium and chloride ions? Just put them in water, right? Okay, then they dissociate. You have Na plus Cl minus. That seems much simpler, doesn't it? Why do we have to melt these things? So could we do an electrolysis in an aqueous solution instead is the question. Alright, so let's do an example here. Let's say we've got the electrolysis of a cell with NaF, okay? And so we want to make pure sodium, pure fluorine gas, okay? And we put that into an aqueous solution. So as soon as we do that, we've basically got three things in the solution, okay? We've got Na plus, we've got F minus, and we've got H2O. Okay? Those are the three things that are in that solution. Does that make sense? So, when we pass electricity through this thing, there are two possible cathode reactions that could take place, okay? And again, we're forcing the electrons in one direction here to try to reduce the sodium, okay? Remember, cathode is reduction, right? Red cat. The one we're wanting to reduce here is the sodium because we're trying to produce pure sodium, okay? So one of the cathode reactions could be Na plus an electron goes to Na. In this case, because we're at lower temperatures, it's going to probably create solid sodium, okay? But what's the other possible cathode reaction that could happen here? Could the fluorine get reduced? F minus probably isn't going to become F2 minus, right? Or F3 minus. That's about as reduced as fluorine can get already, okay? So then our only other option is the H2O, right? Now if you look at your chart, the reduction of H2O is fairly far down the chart. Do you guys see that? It's 2H2O plus 2 electrons yields H2 plus 2 OH minus. Does everybody see that on the chart? Now there's two places where H2O is on the chart, but you have to look where it's a reactant, right? Are we seeing that? Okay. So that's the other possibility, is that you could have this 2H2O liquid plus 2 electrons yielding H2 gas plus 2 OH minus. Okay, now let's look at the reduction potential for both of those. Okay, the reduction potential for the sodium Na plus going to solid Na is negative 2.71. And the reduction potential for the water is negative 0.83. These are volts. So, if we're passing a current through this thing, which one of these two is going to actually get reduced here? Which one has a higher reduction potential? The water, right? Oh, well, that's a problem. So we pass electricity through this thing when it's in water. We're reducing the water, not the sodium, unfortunately, okay? So that's a problem because now this doesn't end up happening, okay? And that's what we were trying to get to happen in the first place. All right, so that kind of explains why we have to do it this way instead. We have to melt the salt. We can't have anything else in there, okay, that might be reduced instead of the sodium, okay? And the same thing's going to happen on the fluorine side. So the one that's actually going to occur is the H2O reaction. The reason we know is because it has a higher reduction potential. Okay? So then, possible anode reactions, okay? Now an anode is the oxidation, right? So we've got F minus, we've got Na plus, and we've got H2O. Those are our three possible species here, okay? Could the F minus get oxidized? Yeah, it could, right? It could lose an electron, become F2, okay? So that's a possibility here. So F minus, Now we have to balance this. It's going to be 2 electrons over here, right? Because it's F2 on the other side. Now the other possible oxidation that could occur, water could also get oxidized, okay? Now, to find where water gets oxidized, we have to look further up on the chart here, okay? Do you see the reduction potential of the oxygen? The oxygen plus the 4H plus 4 electrons yields 2 H2O liquid, okay? So we have to write that in reverse to think about oxidation, okay? So this is kind of tricky, but let's write it this way. So the 2H2O liquid could be oxidized to produce O2. Okay, so those are the two possible oxidation reactions. Now, on our chart, again, this is a little bit tricky, okay? We're not going to be thinking about this in terms of reduction now. We're going to be thinking about this in terms of oxidation, okay? Or I guess we could think about it in terms of reduction if I wrote both of these backwards, okay? But this is the way that they're really going to occur, so let's think about them this way, okay? If I flip this reaction around like this, what do I have to do to the E as it's listed on the chart here? Right, because we're talking about oxidation as the opposite process, right? So if the reduction potential of fluorine gas is 2.87 volts, then to get it to go in the other direction, negative 2.87 volts. In other words, it's going to require 2.87 volts to make that occur. Does that make sense? We have to put that many volts into it, okay? And now notice I didn't write red down at the bottom, reduction, because we're not talking about reductions here, we're talking about the oxidation voltage, okay? And then this one, because again I flipped it, this is going to be negative 1.23. Okay, so in other words, the one that's going to get oxidized first, the one that's going to get oxidized most readily is the one with the highest voltage when we're writing this in terms of oxidation, okay? This one, the water, again, takes less volts to oxidize than the fluorine. Does everybody see that? It's a little tricky because we're kind of writing it backwards from the way it's on the chart, okay? But again, water's going to mess us up. The water's going to get reduced and oxidized before the fluorine or the sodium, okay? So we don't end up doing either of the things that we were trying to do here. All we do is make some hydrogen gas and some oxygen gas. Okay, which again is kind of useful, but not if you were trying to make solid sodium and fluorine gas, right? So the one that's actually going to occur is this one. Takes less voltage to oxidize. or you could just say it's more easily oxidized. Okay? Point is, we can't do it that way. We've got to melt these things so there's nothing else in there. We can't have water in the solution because water's going to mess it up. Okay? Minimum EMF needed to make this electrolysis happen. How strong does the voltage on our battery have to be, in other words? Okay? So, again, this electrolysis, now we can sort of think of it as we're oxidizing and reducing water, and the sodium fluoride is in there to provide some ions so that so that current can flow through the solution. Okay, so now we were initially starting with this, trying to make solid sodium and fluorine gas. Now the NaF is just in there so that we can aid the process of making the H2 gas and the O2 gas. And we want to see how strong does the voltage on our battery have to be in order to make this occur. Okay, so we already talked about the cathode reaction here. You know what? I don't think this is one of those places I think we need to skip, because we've got to get to this last part because they will talk about that. All right, so we're gonna skip this. Maybe we'll have time to talk about it in class, maybe not. But I'm not sure that this. And then I'm looking at this one: electrolysis of AgF in acidic solution leads to the formation of silver, metal, and oxygen gas. Write the half reaction that occurred. Okay, now this might be useful, writing the half reactions that occur at each electrode, but again, calculating the minimum external EMF required. I've never seen that kind of question on an AP test, so I'm not going to talk about that now. Okay, so let's just do part A here, because then we can think a little bit more about what's happening with electrolysis. Okay, so we've got an AgF solution. Okay, and there's also, it says it's an acidic solution, so that's nice. We've got some acid H plus ions there present in case we need them. It leads to the formation, and it's even telling us what's happening here, the formation of silver metal and oxygen gas. Okay? It's interesting. Where's the oxygen gas coming from? Okay, this is aqueous, right? So we have some water in that solution. So once again, we are messed up a little bit by the fact this is in water. If we were trying to make fluorine gas, that's just not going to happen here, okay? But we are going to make some silver metal. That seems kind of useful, right? So, essentially, one of the things that's happening here is the Ag plus is being converted into silver, right? Solid silver. Now, in order for that to occur, so I can leave myself a room here, but in order for that to occur, what has to be happening to the Ag+? Is it being reduced or oxidized? It's being reduced, right? Okay, so we're adding an electron here. All right, so if that's being reduced, then this reaction is taking place at the cathode or anode? Cathode, right? Red cat. So this is the cathode reaction. Okay? And then the other thing that gets produced is oxygen gas. Okay? So that reaction would be the 2H2O yielding, and again, this is on your chart, so that's how you would know how to write this half reaction. Yields O2 gas plus 4H plus 4 electrons, okay? And again, because the electrons are being given off here, this is the oxidation, so this is the one that's happening at the anode. Okay? So the net result of this is we make solid silver and oxygen gas. Okay? Now, they could ask you to add those two together and tell the overall equation. If they asked us to do that, we'd have to multiply the top one by 4, right? In order to make the electrons balanced on both of these. Okay? But that's the idea here. When we pass electricity through this, we can cause these things to happen in a way that they wouldn't normally occur. All right? Actually, this first one up here, if you have Ag plus in a solution, it doesn't take much to turn that back to solid silver. You can put almost anything in that solution, and it will take electrons from it. Okay, because silver would prefer to be in its natural state. That's why it's a precious metal, because it doesn't usually react with other things. Okay. All right. So far we've only seen electrolysis where the electrodes were inert or unreactive. They were simply on the surface. I'm just going to mention this. We're not really going to do any problems associated with this because, again, we've got to get to the last part. The electrolysis stoichiometry is the part that you probably will see at some point on the AP exam. Okay. So electroplating, you use active electrodes, and all that means is electroplating, you might do this when you're trying to coat a metal with something on the outside that would be useful for it. Okay, an example of that, nickel on steel. Now this is just a general, this is all I could really find as far as a picture. I couldn't find one specifically for nickel and steel, okay? But this is an example of one that you might do. If you put steel electrodes into a solution here and you electrolyze it, when you've got some nickel solution and I2 plus ions running around in here, you can actually cause the nickel to solidify on the outside of the steel. Now, why might that be useful? Maybe a couple of reasons. Well, okay, you're not really in the home decorating phase of your life right now. But when my wife and I first moved into our new house, it's an older house, and so she looked at everything that was gold, and she's like, this has all got to go, right? Like all the gold doorknobs, all the gold fixtures, lamp fixtures, and all that stuff, okay? And one of the things that she kind of likes is like the brushed nickel look, okay? So you can kind of get that if you can plate the nickel on the outside of maybe another metal, okay? Because maybe you don't want the whole thing to be made of nickel. Maybe you want the properties of steel, but you want the look of nickel. Does that make sense? So you just plate that on the outside, okay? Or maybe you are worried about the steel corroding, because steel is primarily made of, do we know? Steel is an alloy that's primarily made of iron, right? And what happens to iron when it's exposed to air for long periods of time? It tends to rust, right? Okay, so maybe this is a way that we could also prevent corrosion from happening, okay? So there's some usefulness to this electroplating, but that's the idea of why we would want that to happen. So all you're doing here is essentially you're passing electricity through, and this is the cathode. You can see this is the negative terminal here, so the electrons are flowing this way in this particular example, okay? So the electrons are flowing through this cathode, and this is the solution, or this is the cathode, sorry, this is the electrode where the reduction is going to occur, okay? So that's where the nickel is going to be reduced, and it would plate out onto this one, okay? And so that's kind of the idea of how that works. But again, I'm not going to worry too much about the possible reactions, the cathode, the overall reaction, and the EMF needed. What we really need to talk about here is electrolysis and stoichiometry, okay? And we've touched on this before, and I don't think this is anything you're going to have too much difficulty with, okay? Because we've talked so much about stoichiometry this year. Might as well end our year on stoichiometry, right? So here we go. If you look at this example right here, the sodium Na plus an electron going to just sodium, okay? You can actually figure out stoichiometrically how much charge you're going to have to pass through a particular metal. Let's say that you want to make 10 moles of sodium, or you know how many grams of sodium you want to make. You can figure out how much current you need to pass through this cell for how much time, and then that'll tell you, how long you have to do it and how much the current needs to be in order for you to get the amount of sodium that you want, okay? Which can be kind of a useful calculation to do if you're trying to figure this out industrially. How much current do we have to pass through this thing and for how long in order to make the amount of sodium that we want to make, okay? So that's why we're doing this process. And so all you have to do here is just look at the stoichiometry, the coefficients in the equation, and that basically tells you the answer to these questions right here. All right, so 1 mole of electrons if we have 1 mole of electrons moving through our system here, that's going to plate out how many moles of sodium metal? Not a trick question, right? It's just 1, right? Okay. If we have 2 moles of electrons, that could plate out 2 moles of sodium metal. All right, and it's all based on the stoichiometry in this equation. Okay, so again, someone industrially looking at this could say, all right, I need 2 moles of sodium metal, so I need 2 moles of electrons to pass through this thing. Okay, and there are ways to figure out, which we're going to talk about in just a second, ways to figure out how much current it takes to get 2 moles of electrons through. Okay. How many moles of electrons are needed to produce 2.3 moles of copper from Cu2+? Okay, well, we can do this just like a normal stoichiometry problem, right? So we've got 2.3 moles of copper is what we want to produce here. So the first thing we'd want to do is convert the copper to the copper 2+, right? Actually, that's not really necessary on this one. Let's just go for moles of copper, because this is in the equation also. What we really want to know is how many moles of electrons, okay? So we can go from moles of copper to moles of electrons because they're both in the equation here, okay? For every 1 mole of copper I want to plate out, how many moles of electrons does that take? Yeah, again, just look at the stoichiometry in the equation. It takes 2 moles, right? So then, you probably didn't need to do this whole process for this, but they do get more complicated. So this would be 4.6 moles of copper. Sorry, moles of electrons. I think I've forgotten how to do stoichiometry. Okay, so it takes 4.6 moles of electrons to make 2.3 moles of copper, because it takes 2 electrons for every 1 mole of copper that we make. All right. Now, a couple of things, just reminders from the first or second set of notes that we took. I can't remember exactly when we talked about this, but a Coulomb, the way that a Coulomb and an amp relate to one another is a little bit tricky, okay? I'm going to try to explain this well. But a Coulomb is how much charge passes a certain point in 1 second when the current is 1 amp, okay? And an amp is actually a certain amount of charge passing a given point in a certain amount of time. So they're actually kind of the flip side of the same coin, all right? So a Coulomb, again, that's how much charge is passing a point in a circuit in 1 second. And the charge on 1 mole of electrons is 96,500 coulombs, okay? So if you have 1 mole of electrons, that's your charge, okay? This is also, 1 mole of electrons is sometimes called a Faraday. All right, so if you see a Faraday on the AP exam, they're talking about a mole of electrons, which contains 96,500 coulombs, okay? So that tells you both, if you have 2 Faradays, that tells you have 2 moles of electrons. It also tells you how much charge there is, okay, that is passing through this thing. All right, so then the formula here, the number of coulombs passing through a cell, you can use the following formula. Coulombs equals amperes times seconds. What I don't have in front of me right now is the equation sheet. And I feel like I need to have this out for this one, because you need to know exactly what you can look at here in order to make these conversions. So let me pull that up quickly. Here, I'm going to freeze this thing for a second, or pause it. Okay. So, just very quickly here, coulombs equals amperes times seconds. The way that that is designated on the AP exam, and I've forgotten that they use the abbreviations here, but the Q is the symbol for coulombs, amperes is I, and then seconds, you know, usually this is just going to be in terms of time, but it needs to be time in seconds, okay? So if you have those 3, you've got Q equals I times T, okay? Now, the way that they show that on the AP exam, on the equation sheet, at least if the equation sheet is in the same format as it was last year, this is what you're going to be looking at. I equals Q divided by T, okay, which is just a rearrangement of that same equation. Now, you don't even have to remember that exactly, because they, over here, on the right side, they tell you that I equals current, Q equals charge, T equals time. Now, because this is a simple equation, I would go ahead and memorize it anyway, just because you don't get the equation sheet on the multiple choice section, okay? So you're kind of going to need to know this anyway, all right? But that's a fairly simple one to remember. The amps equals the coulombs over time, okay? And so if you know that formula, that's going to help us out here, okay? So here's my little chart. It's not mine, it's from the book, but I thought it was good, so you probably want to reproduce this on your notes. And it might be worth just kind of thinking about this, but let's say that we want to know a certain number of grams of a substance we can make. So down at the very bottom here, that's kind of our end goal, all right? So we need to know how much current in amps we need to pass through this thing. And usually what they'll say is, they might say something like, how many grams of a substance can be produced in this amount of time if this is the current we're passing through the electrolytic cell, okay? So you're starting with current, and they'll hopefully give you an amount of time, all right? So what you would do there, you would just multiply by time. And again, here, to get from the current to the charge, I would just remember the I equals didn't I just say Q over T? Yeah, I equals Q over T. Okay. Did I do that right? I'm doubting myself here. I need to make sure I get this equation right for you. Yeah, I equals Q over T. Okay, that's right. Okay. So if you remember the I equals Q over T equation, which I obviously just didn't, then you should be able to get from current to charge, okay? So you don't necessarily have to remember that particular part of the equation, okay? That will help you to do this step, okay? But basically, if you're given the current, you can multiply by the time, and that will give you the charge, okay? Once you have the charge in coulombs, you can figure out moles of electrons, which again is the same thing as Faraday's, okay? And all you have to do there is just remember that 1 mole of electrons is 96,500 coulombs, okay? So that'll tell you moles of electrons. Once you have moles of electrons, now you can just use the stoichiometry and the balanced chemical equation to figure out the moles of the substance being oxidized or reduced, and then you can use the molar mass to convert to grams, okay? This seems complicated. It's really not that bad, okay? So we're going to run through a couple of examples here just to make sure we've got this process. You need to know how to do this part. This part's important, okay? All right, so did you guys have the chart copied down? Sorry, I know that was a long chart. All right. So calculate the number of grams of aluminum produced in 1 hour by the electrolysis of molten AlCl3 if the electrical current is 10.0 amps. All right. First rule, stoichiometry. Now we're going way back. Balanced chemical equation, all right? So let's do that. We're electrolyzing molten AlCl3, okay? So we want to know the grams of aluminum produced. So that's the half reaction we really care about right now, okay? So if we have molten aluminum, that means that we have Al3 plus to begin with, right? And this is going to end up being converted into solid aluminum. Okay, so Al3 plus 3 electrons, because this actually, the aluminum needs to be reduced in this process. It's going to give us solid aluminum. Okay? So there's our balanced chemical equation that we need for this reaction. Does everybody understand where that came from? Okay, look at what they're asking you for. They're asking you for aluminum, so that's the half reaction that we care about here. All right? I'm starting with 10.0 amps. Okay, so one of two ways here. You can use the I equals Q over T equation that you have, which maybe that's the best way to do this, just because that's what you're going to be able to do if you have the equation sheet in front of you. So you don't have to memorize that whole chart that I just gave you. I think it's useful, but so again, one of two ways. If you remember I equals Q over T, That's going to tell you, oh, okay, I need to multiply my charge by my time in order to get to Q, right? So then I'm going to multiply this by my time. Now my time needs to be in seconds for this equation to work. Okay, so 1 hour is, we know how many seconds are in an hour? 3,600, right? 60 times 60, so 3,600 seconds. Okay, that's going to give us our coulombs. Okay, where's my calculator? Why do I need a calculator for that? Is a better question. Okay, so 36,000 now. That's the number of coulombs we have. Okay. Now, to get from coulombs to moles of electrons, we just need to remember, and this conversion also, I meant to show you this on your, this is going to get rid of all my stuff here. I'm going to keep it this time. So if you look on this equation sheet also, I believe they give you a conversion for coulombs. Yeah, here it is. Down here, Faraday's constant F equals 96,000 coulombs per mole of electrons. Okay? So there are 96,500 coulombs in a mole. So to get from coulombs to moles, we just need to use that conversion. All right? So we go back over here. We got 36,000 coulombs, okay? And then we're just going to say that there are 96,500 coulombs in 1 mole of electrons, okay? Now we've converted to moles of electrons. Now we're just doing stoichiometry. So now we go from moles of electrons to, what are we trying to figure out here? Right, so we're going to go to moles of aluminum first so that we can get to grams of aluminum, okay? 3 moles of electrons for every 1 mole of aluminum here. We're going to go from moles of aluminum to grams of aluminum, and that you have to use the periodic table for. It's 26.982, about 27. So then you just work that process through, okay? It's just a basic stoichiometry problem from there. And you end up with 3.36 grams of aluminum. Hmm. 10 amps for 1 hour makes 3.36 grams of aluminum. That doesn't seem like an incredibly efficient process, right? We'd probably need to increase the amperage there in order to have any hope of making this industrially, okay? And there might be better ways of purifying aluminum than this, but this is one way, okay? All right, in the electroplating of copper, 1.20 Faradays of electrical charge are passed through a CuSO4 solution. What mass of copper would be deposited on the cathode? Okay, so once again, we want to know how much copper is going to be made here. Now we've got a solution of CuSO4. Okay, so again, first rule on these problems, balanced chemical equation. Okay, as soon as, because we are told this is a solution, we can know that we've got Cu2 plus ions and SO4 2 minus ions, right? Which of those ions are we concerned with in this problem? The copper, right? Okay, so we need to look at copper 2 plus. And again, in order to make copper, we're assuming solid copper here. So this is a reduction process. Now, if we weren't sure that this was a reduction process, this is being deposited on the cathode. Cathode equals reduction, right? Okay, so there's our balanced chemical equation for this one. Now, 1.20 Faradays of electrical charge. What did I say that a Faraday essentially is? That's the moles of electrons, okay? So when you see Faradays, you need to think moles of electrons here. So in other words, we're starting with 1.20 moles of electrons. This one's actually easier than the other one because we don't have to worry about the amps to coulombs, coulombs to moles of electrons part. We're already there, okay? So now if we've got 1.20 moles of electrons, then we just go from moles of electrons here to moles of copper. 2 moles of electrons for every 1 mole of copper. We actually did that earlier. And then we're going to go from moles of copper to grams of copper. And that is 63.546. So once we work that out, going to get about 38. 3 sig figs, 38.1 grams of copper. Okay. Does that kind of make sense how that works? Okay, it's not that difficult of a process really once you get it, and it's all on your equation sheet, so that'll help you out. Okay. All right. That is it for the year. See you guys in class.